The 40% water world. LHS 1140b holds up to 20% of its total mass in liquid water, making it a liquid powerhouse that puts Earth's measly 0.02% to shame. For years, we debated if this was a mini Neptune wrapped in a suffocating hydrogen envelope or a rocky super-Earth. New transmission spectroscopy from JWST's latest cycle has finally settled the score. We are looking at a massive Hycean world with a nitrogen-rich atmosphere, stripping away the gas giant label for good. This is the first time we have identified a secondary atmosphere on a temperate world that actually resembles our own. But the real shock lies in the density measurements that rewrite the planet's internal structure. Breaking the gas giant myth. We used to think planets this size were destined to be failed. Neptunes, holding onto thick, toxic layers of hydrogen and helium that crush any hope for life. But LHS 1140b is too dense for that. The latest data reveals a planet that is about 6 times the mass of Earth, but only 70% larger in diameter. This specific ratio points to a solid core and a deep, global ocean rather than a bloated gas shell. By excluding the low-density hydrogen model, we have confirmed that this world didn't migrate from the outer system. It formed right where it needed to be. This structural stability is the key to why its atmosphere didn't just blow away, and that leads us to the specific chemicals we just found. The nitrogen signature. Oxygen is the headline grabber, but nitrogen is the real indicator of a stable, Earth-like environment. JWST just detected a high mean molecular weight atmosphere on LHS 1140b, which is a way of saying it is dominated by heavy molecules like nitrogen rather than light gases. This is a critical distinction because it prevents a runaway greenhouse effect and provides the surface pressure necessary for liquid water to exist without boiling off into space. It is the difference between a Venus-style hellscape and a habitable harbor. This chemical fingerprint suggests the planet has successfully recycled its volatiles through a geological cycle. That geological activity leads us to the most controversial comparison in modern astronomy: why TRAPPIST is losing. For a decade, the TRAPPIST-1 system was our best bet, but those planets have a radiation problem. Their star is an active, angry red dwarf that likely stripped their atmospheres billions of years ago. LHS 1140 is different. It is a quiet, older star that emits significantly less ultraviolet radiation. This means LHS 1140b has been sitting in a calm zone for 5 billion years, allowing its nitrogen-rich air to stay put. While TRAPPIST planets are likely bare rocks or scorched deserts, this world has the shielding required for long-term biological evolution. It is the most stable real estate we have found in the habitable zone. But the planetary location is only half the story. The real power is in the energy balance, the new baseline for habitability. The data from LHS 1140b forces us to abandon the idea that Earth-sized rocks are the only candidates for life. By proving that a massive Hycean world can maintain a nitrogen-dominated atmosphere, we have expanded the habitable zone's definition to include planets with vastly different pressures and gravity. This shift moves our focus away from the Earth twin obsession and toward Earth-plus scenarios where liquid water is more abundant and atmospheres are more resilient. In the search for biosignatures, LHS 1140b has leapfrogged over every other candidate because its stability is no longer a theoretical model but an observed reality. We are no longer looking for a needle in a haystack. We are looking for more oceans in a nitrogen-rich galaxy. This discovery changes the target list for the next generation of direct imaging telescopes. Watch for the Habitable Worlds Observatory mission profile to pivot toward these super-Earth targets by late 2026. Subscribe for more.